Think I am live on YouTube and I should be live on Twitch also. Well, am I live on Twitch? Yep, I am live on Twitch and on YouTube. YouTube. Um, refresh. Shit. Till no. Okay. Here it says that I am live. Um, even in my death. Yep, I'm live. It is just not showing here. Yep, I'm live. Okay. So for today, we are going to start chapter 3 of this book again. Because now we can write programs in assembly, and I saw that in the exercise of fifth chapter in this book, they are telling us to write programs in Arch assembly. So then we will practice. And for now, after writing a few programs in assembly, let's freshen up our knowledge. And what should be the target for this stream? Um, well, I guess completing the chapter 3 whole as a whole would be a good thing because more than half of it I have already read, and so this would not be a big deal to complete this chapter. Right? The part of computer architecture related to programming is referred to as the instruction set architecture. The ISA is a contact between hardware and software. It defines the set of instructions and the set of registers that the hardware must support. How the hardware actually implements the ISA is called the microarchitecture. Makes sense, and it is not defined by the ISA. Yes. Assembly programmers can write code that will work across a spectrum of different processor implementations as long as the software and hardware are both built around the same ISA. They will be compatible. The ISA is an effective interface between hardware and the data paths and processing elements and software because it creates an abstraction that allows each side to be imagined to function independently. Okay, ISA is a specification about how the processor should work and what the registers it will contain, and the processor manufacturers can then just implement it however they want. They just have to meet the ISA specifications, and it is up to them how they meet those specifications. The first step in learning a new assembly language is to become familiar with the ISA. For most modern computer systems, data must be loaded in a register before it can be used for any data processing instruction. But there are a limited number of registers. Memory provides a place to store data that is not currently needed. Program instructions are also stored in memory and fetched into the CPU as they are needed. This chapter introduces A64, the 64-bit ISA for AArch64 processors, is ARM ARM architecture for 64-bit processor, CPU components, and data paths. The CPU is composed of data storage and computational components connected together by a set of buses or wires. The most important components of the CPU are registers, where data is stored, and the arithmetic logic unit ALU, where arithmetic and logical operations are performed on the data. Many CPUs also have dedicated hardware units for multiplication and or division. Figure 3.1 shows a conceptual view of the major components of an ARch64 CPU and the buses that connected the components together. These buses provide pathways for the data to move between the computational and storage components. The organization of the components and buses in a CPU govern what type of operations can be performed. Yep, it is what type of operations can be performed. The set of instructions and addressing modes available on the ARch64 processor is closely related to the architecture shown in figure 3.1. Okay, the architecture provides for certain operations to be performed effectively, efficiently, and this has a direct relationship to the types of instructions that are supported. Okay, uh, architecture is made in a way to make to perform some tasks efficiently, and that dictates what kind of instructions will be supported by the architecture. Okay, now we have general purpose registers, an ALU unit, a P state, that is the program state, and we know it has four flags: negative, N, 0, Z, overflow, V somehow, and we have one more. We have negative, 0, negative, 0, overflow, and one more, negative, 0, overflow. Should we have four flags? Negative, 0, overflow, carry, and carry, C. The four flags that can be stored in the P state register. Then we have a bus which connects general purpose registers with ALUs, and instruction register with program counter, address register, address bus, and input output and memory. AArch64 architecture provides a set of registers that can be used by programmers to store data. There are limited number of registers, so large programs must store data in memory most of the time and bring that data into a CPU register to be processed. Results of the processing must be moved back to memory to free up registers to process more data. AArch64 user registers, as shown in figure 3.2, the AArch64 ISA provides 31 general purpose registers, okay, which are called X0 through X30. These registers can each store 64-bit of data. To use all 64 bits, they are referred to as X0 through X30. Capitalization is optional. The X can be capital or small. To use only the lower least significant 32 bits, they are referred to as W. W is means a word, and a word is 32 bit long in AArch64. Since each register has 64-bit and name and a 32-bit, we use RO through R30 to specify a register without specifying the number of bits. For example, when we refer to R12, we are really referring to either X12 or W12. Right? Registers from 0 to 7, they are for passing parameters, or scratch registers volatile. Then X8 to store some instruction, caller, saver, scratch registers volatile. And then we have some special registers, X16, 17, 18, PR, something. Then we have LR, link register. We have program counter, we have P state, which stores 4 bits. General purpose registers. The general purpose registers are each used according to specific conventions. These rules are defined in the application binary interface, ABI. The AArch64 ABI is called AAPCS64. The difference between poly saved and caller saved registers will also be explained in section 5.4. Okay, it will come later. The application binary interface. The application binary interface is the interface provided by the operating system. And APCS, the okay, these rules are defined in the application binary interface because the applications, that is any application that is running on your computer, has an interface which it accesses through binary code, zeros and ones. Registers R0 through R7 are used for passing arguments when calling a procedure or function register, or function registers R9 through R15 are scratch registers and can be used at any time because no assumptions are made about what they contain. They are called scratch registers because they are useful for holding temporary results of calculations. Registers R16 to R29 can also be used as scratch registers, but their contents must be saved before they are used and restored to their original contents before the procedure exits. And restore to their original contents before the procedure exits. Okay, some of the registers have alternative names. For example, X16 is also known as IPO. Most of these alternative names are only of interest to people writing compilers and operating systems. However, two of these registers are of interest to all AArch64 programmers. Frame pointer. The pointer X29 is used by high-level language compilers to track the current stack frame. Stack frame, okay. This register can be helpful when the program is running during a debugger and sometimes help the compiler to generate more efficient code for returning from a subroutine. The GNU-C compiler can be instructed to use X29 as a general purpose register by using the format frame pointer command line option. The use of X29 as the frame pointer is a programming convention. Some instructions, example branches, implicitly modify the frame counter, the link register, and even the stack pointer. So they are considered to be hardware special registers. As far as the hardware is concerned, the frame pointer is the exact same as the other general purpose registers, but Arch64 programmers use it for the frame pointer because of the ABI, application binary interface. Okay, so ABI says that you can use the frame pointer register, which is the 29th register, and this register is helpful when the program is running a debugger. Current stack frame. Yo, P state register. The P state register contains bits that indicate the status of the current process, including information about results. Oh yeah, let's see what is frame pointer. Is pointer register in R64. In R64 assembly, okay. In R64 assembly, the frame pointer register is a general purpose register used in stack frame management during function calls. Traversal. It helps simplify stack traversal debugging by providing a stable reference point within a function's stack frame. Within a function's stack frame. Okay. Register name 2929 x29 aliases often referred to as the frame pointer fp purposes points to the base of the current stack frame remains constant throughout the execution of the function even as the stack pointer sp changes used to access local variables and saved registers within the stack frame. How it works. Functions prologue entry. The current value of the frame pointer 29 is saved on the stack. X29 is updated to the current value of the stack pointer SP, establishing the base of the new stack frame. This ensures that X29 is always points to the start of the function's stack frame. Function epilogue exit. The original value of X29 is restored from the stack. The stack pointer SP is adjusted to its value before the function call. Accessing variables using offsets from X29. A function can access its local variables and parameters stored on the stack. Okay, so stack pointer goes up, but uh, frame pointer does not. Here is a simple example of how X29 is used in a function. Okay, STP, save X29, old frame register, and X30 LR link register on the stack. This on the stack. Move SP on into this. Update X29 to point to the new stack frame base. Function body accesses variables during offset from this epilogue. LDP load pointer store pointer. Okay, restore x29 old frame. And how do I store 69 and 30 LR and adjust SP return to the caller. Definitions of using frame pointer, easier debugging, consistent frame references even when SP changes. Example, dynamic stack allocation 29 remains stable. Optional use. Modern compilers often omit the frame pointer for optimization using SP directly instead, but it can be established. Example with this in GCC for easier debugging. In summary, X29 saves a fixed reference for the stack frame and making stack management and debugging more straightforward in R's assembly. Yes. So, um, does this mean that whenever a function is called, then the address for the first instruction of that function is added to the stack pointer and the frame pointer is also updated? But during the execution of the instructions instructions in that function, the stack pointer may move forward, but the frame pointer remains at its place, and we can thus access its address to uh, get the values in the stack by providing an offset from the address stored in the frame pointer. Is that correct? Yes, your understanding is correct. Let's break this down step by step. When a function is called, return address saved. The return address, the address of the instruction the program should return to after the function is stored in the link register 30. Often the return address is also saved on the stack along with the old frame pointer, okay, as part of the function prologue. Okay, stack pointer and frame pointer updated. The current frame pointer x29 is saved on the stack to preserve the caller's stack frame. The stack pointer sp is decremented to allocate space for the new stack frame. Is decremented to allocate space for the new stack frame. The frame pointer x29 is updated to point to the current stack pointer, marking the start of a new stack frame. During the function execution, stack pointer moves. The stack pointer may be adjusted further, example, to allocate space for local variables or temporary data. Frame pointer stays fixed. The frame pointer x29 remains constant, pointing to the base of the stack frame established at the beginning of the function, accessing values in the stack. Local variables and saved registers can be accessed using fixed offsets from the frame pointer, making it easy to retrieve them regardless of how the stack pointer changes. Example walkthrough prologue. Store pointer into this, and somehow this. Save old frame pointer and link register on the stack. Okay, I'm storing this and this into this, and then updating the stack pointer also because of this. And why is it getting minus? It is getting minus because stack grows downward, and higher addresses are here and lower addresses are below. So stack grows from higher addresses to lower addresses. It is counterintuitive, but that is how it is done. Now, move moves the value in the stack pointer, current value in the stack pointer, onto into the frame pointer, STP, stack 29 and 30. Okay, decrement the stack pointer by 16 bits. By decrement, they mean to increase the stack because the first address is a higher address and then it is in descending order. The addresses are in descending order. Store the old frame pointer x29 and return address x30 on the stack. Update the frame pointer to point to the new stack base. Accessing variables. Suppose the function allocates local variables and their offsets are this 29 local variable 1 and x29 local variable 16. So yes, instructions can use these offsets to load and store values. Yes, epilogue. And after the function is done, then we load the new values into the stack pointer and then increment the stack pointer. That is just go back, decrease the stack pointer, decrease the size of the stack, and then return. This will take us to the address that is stored in this linker register. Load the old frame pointer x29 and link register x30 from the stack. Adjust the stack pointer SP by 16 bytes to remove the stack frame. The frame pointer x29 is a fixed reference point within a function's stack frame. The stack pointer SP may change dynamically during the function's execution, but x29 stays constant. By using the frame pointer and offsets, you can reliably access stack data, local variables, saved registers, etc. throughout the function's execution. This approach simplifies stack management and allows for easy traversal of stack frames when debugging. Makes sense. Laptop is charged. Ah, too much power. Yes, now is it visible here? Oh, I gained subscribers. 5 more subscribers. Crazy. Okay. Now, P status register. The P status register program state contains bits that indicate the status of the current process, including information about the results of previous operations. Example 3.3 shows all of its bits. The dashed lines indicate unused space that may be reserved for future AArch64 architectural extensions. The P-state register is actually a collection of independent fields, most of which are only used by the operating system. User programs make use of the first 4 bits, negative, zero, carry, and overflow. These are referred to as condition flags fields. Most instructions can modify these flags, and later instructions can use the flag to control their operation. Their meaning is as follows. Negative. The bit is set to 1 if the string result of an operation is negative, and to 0 if the result is positive or 0. Negative, it is 1 when it is negative, and 0 when it is positive or 0. 0, the 0 flag is set to 1 of an operation is 0. Um, this bit is set to 1 if the result of an operation is 0, and set to 0 if the result is non-zero. Carry. This bit is set to 1 if an add operation results in a carry out of the most significant bit, or if a subtract operation results in a borrow. For shift operations, this flag is used to the last bit shifted out of the shifter. For addition and subtraction, this flag is used if signed overflow occurs. The procedure link register. The procedure link register X30 is used to hold the return address of the subroutines. Certain instructions use the program counter to be copied to the link register, then program counter is loaded with a new address. The branch and link instructions are briefly covered in section 3.5 and in more detail in section 5.4. The fifth chapter is going to be a banger, I guess. The link register could theoretically be used as a scratch register, but its contents are modified by hardware when a subroutine is called. In older in older to save the correct address. Using X30 as a general purpose register is dangerous and is strongly discouraged. Stack pointer. The program stack was introduced in section 1.4. The stack pointer SP is used to hold the address where the stack ends. This is commonly referred as the top of the stack. On most systems, the stack grows downwards, and the stack pointer really refers to the lowest address in the stack. The address where the stack ends may change when registers are pushed onto the stack or when temporary local variables, automatic variables, are allocated or deleted. The use of the stack for restoring automatic variables is described in chapter 5 is going to be a banger. The stack pointer can also be modified or read by a small set of instructions. Zero register. The zero register ZR can be referred to as a 64-bit register. XZR or a W or a 32-bit register with WZR. It always has the value 0. Most instructions can use the 0 register as an operand, even as a destination register. If this is the case, the instruction will not change the destination register. Okay, the instruction will not change the destination register. However, it can still have side effects, including updating the P state flag based on the ALU operation and incrementing a register in pre-indexed or post-indexed addressing. The zero register cannot always be used as an operand. It shares the same binary encoding with the stack pointer. That is, it has which has the value 31 x31. Binary encoding as the stack pointer. Therefore, some instructions can access the zero register while others can access the stack pointer. Program counter. The program counter PC always contains the address of the next instruction that will be executed. The processor increments this register by 4 because one instruction is of 4 bytes automatically after each instruction is fetched from memory. By moving an address into this register, the programmer can cause the processor to fetch the next instruction from the new address. This gives the programmer the ability to jump to any address and begin executing code there. Only a small number of instructions can access the PC directly. For example, instructions that create a PC relative address such as ADR and instructions that load a register such as LDR are able to access the program counter directly. Instruction components now. The ARch64, the ARch64 processor supports a relatively small set of instructions grouped into four basic instruction types. Many instructions have optional modifiers, which result in a very rich programming language. The following section gives a brief overview of the components which are common to instructions in each category. The individual instructions are explained later in this chapter and in the following chapter. Setting and using conditional flags. As mentioned previously, pstate contains four flag bits. Uh, four flag bits. It's 28, 31. Oh, which can be used to control whether or not certain instructions are executed. Most of the data processing instructions have an optional modifier to control whether or not the flag bits are set when the instruction is executed. For example, the basic instruction for addition is add. When the add instruction is executed, the result is stored in the destination register, but the flag bits in P state are not affected. However, the programmer can add the S modifier adds to the add instruction to create the adds instruction. When it is executed, This instruction will affect the NZCV flag bits in the P state. The flag bits can be used to control subsequent branch instructions. The meaning of flags depends on the type of instruction that was most recently used to set the flag bit. Figure 311 shows the names and meanings of 4 bits depending on the type of instructions that set or clear them. Many logical and arithmetic instructions support the S modifier to control setting the flags. Many logical and arithmetic instructions support the S modifier to control setting the flags. Okay, many instructions have the S modifier to control setting the flags. If you add an S at the end, that is state, I guess, then you can control the instruction's behavior to affect the P state register. The register was greater than 64-bit. Result was greater than 64-bit. The signed twos complement returns result requires more than 64 bits, indicating possible corruption of the result. Well, I can use these EQ, not EQ, high, unsigned, high, SS, unsigned, high are same. C equal to 1, C equals 0, C is C the last one. Because if it is, then why is this 0? Okay, these are the things. Uh, I can check the states that it can be. Wait a minute. 4 bits, it can be in 16 possible states. Now, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, and 18 somehow. There are 18 states. Are the states copying themselves? Yep, this one and this one are the same. C0. C0 might mean unsigned lower, and C0 will also mean this state and no unsigned overflow. Very clear. The branch instruction B is one instruction that can have a conditional condition modifier appended to the mnemonic. If present, the modifier controls at runtime whether or not the instruction is actually executed. Table 3.2 shows the condition modifiers that can be attached to the branch instruction. For example, to create an instruction that only branches if the Z flag is set, the programmer would add the EQ condition modifier to the basic B instruction to create the BEQ instruction. There are a few other instructions that can be used to that can use the condition modifier to control their execution using the flags. Immediate values. An immediate value in assembly language is a constant value that is specified by the programmer. Some assembly languages encode the immediate value as part of the instruction. Other assembly languages create a table of immediate values in a literal pool stored in the memory and insert appropriate instructions to access them. ARM assembly language provides both methods. Immediate values can be specified in decimal, octal, octal, hexadecimal, or binary. Octal values must begin with 0 and hexadecimal must begin with 0x. Likewise, immediate values that start with 0b are interpreted as binary numbers. Any value that does not begin with 0, 0x, or 0b will be interpreted as decimal value. There are two ways that immediate values can be specified in GNU ARM assembly. The first way is a literal immediate value. This can be optionally prefixed with a pound sign for clarity. Pound sign and then immediate value or symbol. The second way is the equal to value syntax, which can only be used with the LDR pseudo instruction. The equal to immediate value syntax can be used to specify any immediate value up to 64-bit or to specify the 64-bit value of any symbol in the program. Symbols include programs labels such as main and symbols that are using .eq and similar assembler directives. This syntax is a pseudo instruction because of the way the AArch64 machine instructions are encoded. For data processing instructions, these are limited number of bits that can be devoted to storing immediate data as part of the instruction. In order to store a full 64-bit immediate value, the linker must be create an immediate pool. Okay, because if our immediate value is small, then we can just use a pound sign and then provide the immediate value. Or if it is big, 64-bit big, then we can provide an immediate value with uh, equal to sign before it. And if we do that, then that immediate value will be uh, sent to a location in the memory uh, called the literal pool, and the program will fetch it during the execution of the instruction. The hash immediate value syntax is used to specify immediate data values for data processing instructions. The hash immediate value syntax has some restrictions. The assembler must be able to construct the specified value only using a certain number of bits of data, shift or rotate and or a complement. For example, arithmetic immediate instructions can also can only use an immediate value that fits within 12 bits. For immediate values that cannot be constructed by shifting or rotating and complementing a 12-bit value, the programmer must use an LDR instruction with the immediate value to specify the value. This method is covered in section 3.4. For immediate values that cannot be constructed by shifting or rotating a complement of a 12-bit value, the programmer must use an LDR instruction with the equal to immediate value to specify the value. That method is covered in section 314. Some examples of immediate values are shown in table 3.3. When an immediate value is necessary, the programmer can always use the hash immediate value syntax. The assembler will emit an error message when an invalid immediate value is attempted. The programmer can catch their code to the can change their code to use the LDR equal to immediate value method instead. Yes, that makes sense, a little sense. Yay. The assembler will emit an error message when the immediate value used with the pound sign is larger than what the assembler can handle. Okay, and then we can use the LDR load register this with the immediate value this from the literal pool. And then summary of valid immediate values. Arithmetic type instructions can take a 12-bit immediate value. Logical instructions can take 13-bit immediate values. Move instruction can take 16-bit immediate values. Piece relative instruction 21-bit, and shift with 6-bit, and oh, 6-bit. How much is 6-bit? 2 power 6, that is 64. Okay, addressing modes. That is the addressing modes. The AArch64 architecture has a strict separation between instructions that perform computation and those that move data between CPU and memory. Computational instructions can only modify registers, not mean memory. Because of this separation between store load operations and computational operations, it is a classic example of load store architecture. The programmer can transfer bit, bytes, 8 bits, half word, 16 bits, or word 32 bits and double word 64 bits from memory into a register or from a register into the memory. The programmer can also perform computational operations such as adding using two source operands and one register as the destination for result. All computational instructions assume that the registers already contain the data. Load instructions are used to move data from memory into the register, and store instructions are used to move data from the register into the memory. Most of the load store instructions use an address, which is one of the six options in table 314. The brackets used in the mode denote a memory access. There are three fundamental addressing modes in AArch64: register offset, immediate offset, and a literal. For addressing modes: register offset, immediate offset, and a literal. Mhm, mhm, mhm. Immediate has two important variants: pre-indexed and post-indexed. The pseudo-addressing mode allows an immediate data value or the address of a label to be loaded into a register and may result in the assembler generating more than one instruction. The following section describes each addressing mode in detail. Register addressing. This addressing method is used to access the memory address that is contained in the register xn or x or sp. The brackets around xn denote that it is a memory access using the contents of the register as the address in memory. For example, the following line of code. The following line of code: LDR X3 this use the contents of register 2 as memory address and load 8 bytes of data starting at the address into register X3. Makes more sense. Copies the contents of register X3 to the 8 bytes of memory starting at the address that is in X2. This is really encoded as an unsigned immediate offset. As an unsigned unsigned immediate offset. This is really encoded as an unsigned immediate offset. Okay, xn or xp is just shorthand notation for 0, 0 respectively. Signed immediate offset. The signed immediate offset, which unsigned and yep, there is no plus or minus. There is just a number. The signed immediate offset, which may be negative or positive, is added to the contents of xn or xp. The result is used as the register of the item to be loaded or stored. For example, the following line of code. This LDUR assigned assigned immediate offset calculates memory address by adding 50 to the contents of the register 1. It then loads 8 bytes of data starting at the calculated memory address into register 0, x0. Similarly, the line this stur x0, 1, and minus, because it is signed, adds negative 50 to the contents of x1 and uses that as the address where it stores the 8 bytes of x0 into the memory. Unsigned immediate scaled offset. Scaled offset. The unsigned immediate offset. The unsigned immediate offset, which may only be 0 or positive, is scaled and then added to the contents of xn or xp. If the register being loaded or stored is a 64-bit register, then the immediate value is scaled by shifting it left 3 bytes. It was making much more sense yesterday. What happened? Okay. Yes. 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 It makes sense. Okay. So if I if the register being loaded or stored is a 64-bit register, then adding one does not mean increasing the address by 1 byte. It will increase the address by 8 bytes, and by shifting the by um, the one to the left 3 times means multiplying it by 8. Therefore, instead of adding just 1 byte to the address, we are adding 8 bytes to the address 8. Likewise, if the loaded or store is a 32-bit, the immediate value is scaled by shifting it 2 bytes. If the word loads or stores, the offset is scaled by shifting it to 1 byte, and for byte stores and load and there is no scaling. Okay, note that the syntax for this addressing mode is the same as the syntax for signed immediate value offset mode, but the set of possible immediate values is different. The programmer does not need to worry about which mode is used. The assembler it just simplifies the offset as an immediate value. The assembler will automatically select whether to use unsigned immediate offset, unsigned immediate signed immediate offset, or unsigned immediate scaled offset mode, depending on the immediate offset value that is specified. The result of adding the scaled offset to the base register is used as the address of the item to be loaded or stored. For example, the following line of code. This calculates a memory address by adding this to the register x1. By adding calculates a memory address by adding this to the contents of register x1, then it loads 8 bytes of the data starting at the calculated memory address into register 0. Similarly, the line this adds is to the contents of x1 and uses that as the address where it stores the 4 bytes of x0. Pre-indexed immediate offset. Pre-indexed immediate offset. The memory address is computed by adding the unshifted. The memory address is computed by adding the unshifted signed 9-bit immediate value to the number stored in xn or xp. Then xn is set to contain the memory address. This mode can be used to step through elements in an array, updating a pointer to the next element of the array before each element is accessed. Pre-indexed. Post-indexed. When okay, in pre-indexed, I provide the brackets and then everything is in the brackets and I have an exclamation mark in the end. But in post-index, I have a bracket which contains the register and then comma and pound symbol and then the immediate value. Register xn or x or sp is used as the address of the value to be loaded or stored. After the load value is loaded or stored, the value in xn is updated by adding the unshifted immediate offset, which may be negative or positive. The mode can also be used to step through elements in an array, updating a pointer to point at the next array element after each one is accessed. Register offset. RM is extended or shifted, then added. RM is shifted or expanded, then added to register this. The result is the address of the item loaded to. Okay, so here I will load the value of first I will calculate the memory address. How do I do that? I will take the address in this and add to that whatever is the number in there, and add to that a number which I get after shifting the number stored in this x1 register by 3 times to the left. That is, it will become 8 times of its original value. So this can be thought of as an index and this as the starting point. This shifts the content of x1 left 3 bits, adds the result to the contents of x2 and uses the sum as an address in memory from which it loads 8 bytes into x3. Recall that shifting a binary number left by 3 bytes is equivalent to multiplying that number by 8. This addressing mode is typically used to access an array where x2 register offset when x2 contains the address of the beginning of the array and x1 is an integer index. The integer shift amount depends on the size of the objects in the array. The integer shift, yeah, depends on the size of the objects in the array. This is convenient when the size of the elements is in an array are powers of 2. For example, the shift would be LSL. This is convenient when the size of the elements in an array are power of 2. For example, the shift would be 3 times for double words, LSL, left shift for 2, 2 for words, and 1 for half words. For any array of structure, this method is only appropriate if the size of the structure is in the array power is a power of 2. Many programs use 32-bit integer words. For example, int C is often 32 bits. The following instruction illustrates how to access the array of words. An array of words where W4 is the register to which the array element indexed by x3 is saved. To store an element from the register x0 into an array of half word, the following instruction could be used. To store an element from register 0 into an array of half word, the following instruction could be used. Store the value which is in this into the register which we get after left shifting the contents of this one time and adding that to x4, where x4 holds the 64-bit address of the first byte of the array and w5 holds the integer index for the desired array item. Subroutines often keep data on the stack, including their return address and local variables if they use them. The following instruction shows how to store a double word variable on the stack. This stores into this whatever are the contents of this and add the contents of x1 after left shifting in it 3 times to the SP to get an address into which the value of x0 will be stored. And the instruction x1 is an offset to the local variable starting from the stack pointer. Stack pointer as the base address and x0 is the value used in the overwrite. The local variable on the stack, if rm is specified in a 32-bit register wm, then the option for sign extension can be applied. The programmer can use either sign extension WSXTW or unsigned extension UXTW. Sign extension and unsigned extensions are used to prevent the values of binary numbers from being bit uh, when more bits are used to present them. Signed extension replicates the signed bit, while unsigned extension only zeros to extend the number. If a 32-bit number register often is used to calculate a memory address, and then it should be signed as this. In this case, W3 is the extended sign extended to become a 64-bit value, then the and then the sign extended value is added to x3 to perform Memory address. The blue one is loaded with the word in memory at the calculated address. Now, literal label. Yo, it's quiet. It's too quiet. You will show your new followers, subs, cheers, and raids actively here. Well, I can filter to get the ones that are active, but none is active. Can I change my bitrate to 3.5, 3500? Maybe I might be just pushing my leg a bit too high, but let's see if that happens. And we'll see, it is still 3000, and I suppose it will increase the quality on YouTube, but it might start lagging it. It might start lagging the thing on YouTube. Okay, let's see. I can see my bitrate here. Well, let it have its time. Okay, wait, it was nope, it was not lagging. It is fine here. Okay, the bitrate is same. Let's see. Come back to it after some time. We will come back to it after some time. You're on page addressing modes. Done. Assign, sign, register, offset, everything. We are on page 65. Label. When using a literal load instruction, an address in memory within 1 MB of the program counter can be calculated. When using a literal load instruction, when I'm using a load instruction, an address in memory within 1 MB of the program counter can be calculated. This is possible because the label address is encoded as assigned offsets from the load instruction. Since instructions are 4 bytes long, the label will be at an address that is a multiple of 4 bytes. Okay, on a binary level, the label's offset is encoded as 19 bits. It is then multiplied by 4, shift by 2, and added to the program counter to obtain label's address. Okay, when using a literal load instruction, it's page number 65. We are on page 65 and we have to go till 80. That is quite a bit. What can help? Okay, step up the game, I suppose, but we cannot let it just slide. Okay, when using a literal load instruction, an address in memory within 1 MB of the program counter is calculated. This is possible before because, okay, I do not understand what this is. Uh-huh, encoded as a sign offset. Can you explain this more elaborately? Yeah, sure, certainly. Let's break down the explanation of literal load instructions in AArch64 into smaller, more detailed steps. Literal load instruction. In AArch64, a literal load instruction is like this. Is used to load a value from memory into a register. We are in load into XT register from literal the address of the value in the memory is the address. Okay. A literal load instruction in AArch64, a literal load instruction like this is used to load a value from memory into a register. A value from memory into a register. Okay. The address of the value in memory is calculated as a relative offset from the program counter. Okay, but the program counter changes. Okay. Addressing range, the offset to the label is encoded in 19 bits. The offset to the label is encoded in 19 bits. Since the offset is relative to the PC and can be positive or negative, it can address memory within 1 megabyte MB from the PC program counter, instruction label, and an alignment. In AArch64, instructions are 4 byte long. This means all instruction addresses are aligned to be instruction addresses are aligned to be a multiple of 4. Example, this 4, 8. Okay, offset encoding. The offset is stored as a signed 19-bit value in the instruction. 19-bit value in the instruction. The offset is stored as a 19-bit value in the instruction. So load this into this, and this will be changed to an offset 19-bit offset. An instruction is 4 bytes. 4 bytes, that is 32. And 32, and I am taking out of those 32, 19 bits. What do I get in remainder? 13 bits. 13 bits to store a register name and an instruction. Okay. To calculate the actual byte offset, the 19-bit value is multiplied by 4. Okay. Left shifted by 2 bit. It represents the 4 byte words to skip. Offset encoding. The offset is a signed 19-bit value in the instruction. Signed 19-bit value, therefore 20. It represents the number of 4 byte words to skip forward or backward relative to the PC. Final address calculation. The memory address of the label is determined by adding this scaled offset to the current value of the PC. Step-by-step explanation. Literal pool instruction format. A typical ASCII literal pool instruction looks like this. XT, the destination register where the value will be loaded. PC, the program counter, current instruction address. Offset, assigned 19-bit offset representing the offset in 4-bit words. Encoding the offset. The 19-bit offset is a signed value, meaning it can represent both positive and negative offsets. Multiplied by 4, shifted left by 2 to get the actual byte offset. For example, offset values in 19-bit. This 511 in decimal, actual byte offset will be 204144. 2044. Calculating the address, the target address. Let's assume the current instruction is at address this. The offset is this encoded into this, and now multiply it by this to get by 4 to get the actual offset. Then the address of the label will be label address equals PC plus offset in bytes. This plus this. Okay. Example of backward offset. It is just minus and multiplied by this and then subtract 2044 from the PC. Why the offset is scaled by 4? Because instructions take 4 byte to be stored. The scaling by 4 left shift by 2 is a compact way to encode larger address ranges. Since instruction in AArch64 are always 4 byte aligned, the offset doesn't need to specify byte level granularity. By encoding the offset in terms of 4 byte units, the instruction can use fewer bits to represent a large range. The instruction can use fewer bits to represent a large range. That makes sense. Addressing range with a 19-bit signed offset minimum value 2 power 19, 1 for sign, and then multiply it by 4, this much byte, and this much byte forward. This gives us a range of about 1 megabyte from the PC forward and backward. Here is the complete assembly code. LDR label, label. It stores this thing. Data stored this much byte forward. The load the load instruction is at this, and the label is at this. The assembler calculates offset in words and code. Uh, okay, okay. So in this uh, label stores the address for the value provided to it, and at the nk a word. Program counter is in the memory, and by doing this, I am storing the value label into the memory and also bringing it into the zeroth register. So at the time, uh, and when doing LDR x0 equal label, I am doing two things. Uh, One, loading the value at the address, loading the value at the address which is stored in the label, and because of the equal to sign, I also have to store that value in the memory, and I also have to store that value in the memory and make an offset which is calculated uh, which is calculated uh, from the program counter. No, you are almost correct, but let's clarify what's happening step by step, particularly regarding the this equal to sign in this key understanding. The equal to sign in this label is a simpler shorthand and does not directly affect the actual instruction in machine code. Here is what it signifies the value associated with label. The label in your example points to a memory address where the data is stored. Memory address where the data is stored. Here, label is the memory address of this. Label is the memory address for the value this. Okay. A similar implementation of equal to label. When you use equal to label, the assembler interprets as load the address of label into the register. Load the address of label into the register. However, AArch64 instructions cannot directly encode arbitrary 64-bit addresses in a single instruction. Instead, the assembler generates the address code to achieve this. Generates the address assembler generates the necessary code to achieve this. Okay, LDR. Okay, 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 okay. It does not. This signifies this tells the processor to load the address stored in the label into the zeroth register, but we cannot directly just store an absolute address into a register. Therefore, we calculate an offset and store that offset. The assembler expands this into two steps. Place the address in a literal pool. The assembler stores the address of label in a literal pool. Stores the address of label or the value of label, a section of memory usually near the instruction. The literal pool is within 1 MB of the instruction due to the 19-bit offset limit. Generate a literal load instruction. The assembler emits an LDR instruction to load the value stored in the literal pool. Example is okay. Expanded example. Here's how the assembler handles it. Input code. This data stored at level. This is the data stored. Label is stored the address for this data in the memory. Address expansion. The address of label address is stored in a literal pool. Okay, literal pool has a quad, which is 8 bytes label address. Okay, the LDR instruction loads the address from the literal pool. Okay, the program has now label pointing to this literal pool pointing to containing the address of label. Okay, so label is a memory cell which contains the address for this. And now we have literal pool which contains the address for label, the cell which contains the address for this. Crazy linking, explanation of the two steps, storing the address in the literal pool. This is where the equal to shorthand comes into play. The assembler decides that the actual address example load address cannot fit directly into the instruction encoding, so it puts the address in the literal pool. Okay. Um, label address. Okay, it puts the address into the literal pool, loading the address into the register. The LDR instruction calculates the offset from the PC to the literal pool and loads the address of label into XR. Okay, okay. So the instruction that is stored in the binary, the instruction itself cannot store the value here. Therefore, that address is stored as an offset. That address is stored in the literal pool because the address is too big for the instruction to store in itself. Therefore, that address is stored in the literal pool, and the literal pool contains things which are an offset from the program counter. So therefore, we in the instruction itself stores the offset. The LDR instruction calculates the offset from the PC and loads the address into this. To summarize to your understanding, when you write this, the address stores the address of label in a literal pool, emits an LDR instruction that points to this instruction in the literal pool. At runtime, the program loads the address of label from the literal pool into the register this. Okay, you can use X0 to access the values stored at the label if needed. So the equal to shorthand is not directly about creating or modifying offset in the machine code. It tells the assembler to generate instructions and store values in a literal pool to load addresses efficiently. Now, if I wanted to store not the address in label, but the value at the address, but the value at the memory location whose address is in label, then I omit the equal to sign. right? Yes, omitting the equal to sign allows you to load the value at the memory location that the label points to, rather than the address of the label. If that makes sense. Okay, okay. Sudo load. That is a literal. Okay, sudo load dash equal immediate value. This is a sudo instruction. The assembler will generate a move instruction if possible. Otherwise, it will store the value of immediate or address of the symbol in a literal pool or literal offstring and generate a load instruction using one of the previous addressing modes to load the value into a register. This addressing mode can only be used with the LDR instruction. An example pseudo instruction and its disassembly is shown, and we are listing this and this. LDR this I want to load into this the value at the address this and then return. So what I will do is um, store this in the literal pool. Disassembly of LDR pseudocode dot text comma 8 dot text plus 08. Okay, and I define a word that is this. That is the second half, it seems, and this one is the first half. Uh, okay, so I have two words. 4 bytes here, 4 bytes here. 048C. Okay. Ah. Okay, so I break, store this instead of storing this thing, this whole number. Here in the instruction itself, I am storing this instruction in the literal pool, which comes right here, and I am storing the address of that literal pool here and telling it that it consists of 8 bytes and is about not about it starts at point text this plus 8 plus 4 and plus 8. This is the starting point of it. Okay, that makes sense. Load and store instructions. Yep. Load and store instructions allow the programmer to move data from memory to registers or from register to memory. The load store instructions can be grouped into the following types: single register, register pair, atomic. Uh, Load and store LDR, load register, STR, store register. These instructions transfer a double word, single word, half word, or a byte from a register to a memory or from a memory to a register. Syntax. Yo, option LDR or STR, either LDR or STR. Size. The size can be B, a single byte, H, half byte, signed byte, signed half byte, signed word, RD, the register address, and the address of the memory. AD is one of the address specified in section 3.3.3. STR cannot use a signed size. Store cannot use signed size. It also cannot use the literal addressing mode. The literal addressing mode where the address is stored in the literal pool. Okay, LDR store whatever is in the memory into this, like move whatever is in memory address this into this, and STR move whatever is in the register into the memory. Examples: load the word 4 byte value from mem 4 into word 4. Set the upper 4 bytes of x8 to 0. uh, load uh, the memory address, oh, load the contents into the first the first 32 bits of the eighth register, the contents of the location whose address is stored as at the fourth register. Store the least significant bits from register this W. Store byte from this into mem2. Okay. A double word, one double word, this, and then update the third register. Okay. +7, like literally +7. Is this scaled or not? Load the double word 8 byte value from memory x3 plus 7 into x5. Then set x3 equal x3 plus 5. Yep, this is post increment, and this seems to be pre increment. First update, then set x. Okay, store half word this into this to memory address 6. Then store this, load the half word. Signed half word. Load the half word from value this into x5 and sign extend it. Sign extend it. Sign, sign, sign extend it. Mm-hmm. All right. This register offset now XP, comma some immediate value. Post, yep, and this is pre. So pre comes inside. Yep, pre has this. Okay, so this one, load the value this from this into this, then, and here also it says then. So I guess this is wrong. It should say that first. Oh, this is correct. This is like absolutely correct. Load store single register unscaled. These instructions are the same as load store single register, except that they only use an unscaled signed addressing mode with an offset range of this to this. -256 to 56 programmers rarely need to use write LDUR unscaled explicitly. The programmer can just use LDR or STR, and the assembler will automatically convert them to LDUR and STUR unscaled when appropriate. Okay. The symbol STUR LDUR register address, then this. The address at some register, and then a value. Immediate value 9 bytes long, and it is signed. The optional size is one of byte, half byte, signed byte, signed half byte, signed word. The addressing mode is a single signed immediate with 9 bits. STUR cannot use a signed size. Cannot use a signed size. STUR cannot use a signed size. That is tragic. Hmm. What is the bit rate? It's 350. And is it lagging on YouTube? It is not lagging on YouTube, but is the quality a bit better? It seems, well, nah, the quality is still shitty. Am I the highest specs possible? Yep. The quality is electricity and wait, the screen is not filling. The screen is not screening. Yeah, the screen is not screening. Huh. I'm not to the totally left as I should be. Oh, is it because there is this space? Okay, okay, okay. Video capture, Mac OS screen, um, scale filtering, no, scaling blend, full screen projection. Did I do some? Ah, shit. This is my stream. What the heck? Yep, that. Ah, shit. How do I get out of it? Full screen projection. Ah, okay. Close the projection. Okay. Yep. And full screen. I'm putting source, screenshot, source, uh, transform, scale filtering. Okay, I will figure this out. But right now, let's do this. Whatever is in the memory location, this comes into this RD register, and when we use a store, whatever is in the register goes into the memory location. This example, load byte from this and extend it. Okay, let me write code for this. Load byte, load the byte value from x5 plus 255, sign, extend it, and store the value in x4 test.s. That is my test. Store the value in the fourth register from memory location x5, 255, W for unscaled. Is this correct? Ah, they told me to store a single byte. STURB, STURB, X4, X5, STUR, SB, signed byte, sign, shit. I'll put like hash. Okay, what is the next one? Okay, I will not see the answer. Store the double byte, double word value into the first register from memory X to one is this. U R okay and double byte. It is by default double byte into this register this comma second register comma minus 256. This should work and store the double word value STR x1 minus 256. Yay! Technically never dies. These instructions are used to store or load two registers at a time. This can be useful for moving registers onto the stack or for copying data. This is what we saw earlier in the frame pointer thingy when we were storing uh, values of two registers at some address, starting at some address. These two instructions are particularly useful for transferring data in a load store architecture because each instruction can move twice as much information as the LDR or this load pair. I was calling it load pointer and store pointer. Before that was wrong. Okay. OP operation, load pair or store pair. Then size is optionally SW for signed words. Okay. Okay. I will only take one word out of these. Right. Load. And the size of this is 4. Size of RT is 4 for WT register and 8 for XT. Okay, the size is 4 for WT in this case and 8 for XT. Okay, because the total thing is amounts to 64 bits, and if you are using two registers, then those 64 bits are divided equally, that is 32 and 32 among two registers. Okay, and now size is optionally this. An address is 7 bits pre-indexed, post-indexed, or signed immediate. Signed immediate X range, just this pre-indexed, post-indexed, or signed immediate. Address immediate XT range. Signed immediate XT range. Okay, this is the amount WT range from this till this. Okay, now examples. The store pair and load pair instructions are commonly used at the beginning of a function and at the end of a function. For example, the following instruction allocates 16 bytes. 16 bytes. That is a lot of memory on the stack by decrementing the stack pointer. Then it stores the frame pointer and frame pointer xt at memory stack pointer, the bottom of the stack, and stores the procedure link x30 at stack pointer plus 8, which completely fills the 16 bytes that were allocated on the stack. Store this and this. This is pre-increment. Therefore, first decrease the stack pointer and start storing these values from bottom up into the stack. That makes sense. The opposite of the previous instruction can also. Okay, let me write the opposite for this. Wait, let me write the not the opposite, but the instruction itself. STP store pair what x29 and x30 frame and is the frame pointer and the link register contents. Store them stack pointer minus 16. It is scaled and yep, that is it. And then LT load LDP load into x29 and into x30. And now I have to, because the stack will shrink, therefore I have to increase it, but I have to increase it afterwards. First, I want the things stored there. So this is how. I think this is right. This is right. This this is right. Because I will be incrementing the stack pointer after I have done the loading. Yes. Here x29 is the set to mem 7 to the to the value at the memory location that whose address is stored at the stack pointer, and x30 is set to mem sp plus 8, the next 8 bytes. Then sp is incremented by 16, essentially deleting the values of x29 and x30 from the stack. Although the bits are still there, they may be overridden by subsequent instructions that store data on the stack. The following assembly program demonstrates two instructions are used together to save restore a pair of registers. In the text section, we are declaring that main is a type of function and main will be available globally, and this is what the main stores. It stores stack store pair. It adds onto stack two things. Then it moves uh, value 0 into the frame stack frame. Okay, into the frame pointer, and then moves value 0 into the stack pointer into the link register. Okay, and then load pair this into this and then return. Like this function essentially did nothing. Store change their contents, store this and this. Okay, the following function assembly code demonstrates two instructions used together to save, store, and restore a pair of registers. The following function demonstrates how to use the store pair and load pair instruction to save and later restore all the non-volatile registers. Okay, store from 16 to 30, everything, and then do your thing here, insert function body here, and then load everything back, just like that in the same sequence, starting from 2930, 2930 branch instructions. Here we are. Yes. I will be back in a minute. Just wait. Yep, I am back. Okay. Um. Hmm. 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 Hello. Right. That is some nice volume. Well, I just came back on YouTube. Okay. Branch instructions. I washed my face. I was feeling sleepy, goddamn sleepy. Okay. Branch instructions allow the programmer to change the address of the next instruction to be executed. They are used to implement loops, if then structure, subroutines, and other flow control structures. There are five instructions related to branching: branch to register, branch and link subroutine calls, compare and branch from compare and branch, just do the branch, no, doesn't matter, just do the branch. Then branch to register, okay, branch to the address that is stored in a register, I guess. Branch and link call subroutine BL, yeah. Also update the link register branch and also update the link register with the instruction that is currently the next. Compare and branch. Compare and only branch if something is something. For program counter relative address. Okay. This instruction is used to perform conditional and unconditional branches in program execution. B. Enough. That is enough information for us. B. It is used for creating loops and if then else constructs. This is the only instruction that may have a conditional suffix attached to the mnemonics. Okay, condition will come here. Okay, the option font, that is condition, can be any of the codes from table 3.2 which were equal, not equal, greater than something, something, a lot of things specifying conditional execution. The target label is the address where the program is the address of the instruction where the program should go next, or the label can be any label in the current file or any label that is defined as .global or .global label in any file that is linked within a certain range. Target label is encoded as a program counter relative offset with 19 bits. Okay, it will be in the address for the instruction will be stored in uh, the address for the instruction will be stored in the literal pool and an offset with 19 bits will be calculated for it, and that offset will be stored in the instruction in the branch instruction conditional branch, and 26 bits for an unconditional branch. Okay, to allocate the correct address, the immediate value is first shifted by left 2 bits and then added to the program counter. The range of target label is +1 minus for conditional and 128 MBs for unconditional branch. That is a lot of MBs. B target address into the program counter. Unconditionally provide new addresses to the program counter PC. B condition. If condition, then program update the program counter with the target address. Conditionally move new address to the program counter. Examples: branch PVS overflow. Okay, a branch to label overflow if the signed overflow flag V is set, meaning if it has value of 1 in the P state register program state. An unconditional branch is always taken. One example is an endless loop. Let's see, text main function global. Okay, branch to the main. Okay, it will branch to the main. It will see that there is a function instruction to branch to the main. It will again branch to the main and just keep the loop will go keep going on and it will never return. Okay, sois, sois. Okay, now conditional branching is often used if the implementation if statement and used to implement if statements and other control flow logic. Store the pointers, store the pair this and this into the stack pointer Now compare this and WZR. What is WZR? Ah, the zero register. The no like the register that stores the value zero. Compare that with W. Now if they are equal, then end if, right? And if they are not equal, then move the value 1 into register this. But they are not equal. Then it will move the value this into the register this first one. Else, and then it will, I guess, go into this thing is and load them back and then return. But if it is one, if it is zero, then it will return word zero. Okay, so it will return one if they are equal and return zero if they are not equal. No, returns zero if it is zero and return one if it is not zero. Okay, branch register. These instructions allow the program counter to be set to the value contained in A64-bit general purpose register. Okay, branch to register and return from RET, that is return from subroutine. It this puts the branch. This updates the program counter to the address that is stored in the XN register and then return. What does the return do? Ret uses the procedural link LR, which is the 30th register if no register is specified. Branch to register. If no register is specified, RET is only used to return from a subroutine. BR can be used for implementing a computed go to switch statement. Like BR, it does the address of XN into the program counter and return. What does it do? By default, it takes the address in X30 into the program counter, or if it is specified, it if a register is specified, it will put in the address of that register into the program counter. Example, the branch register instruction will set the program counter to the contents of the register. This that is very simple, and this can generate a segmentation fault if the contents of X10 are invalid. If not, the processor will begin executing instructions at the address contained in X10. The return from procedure instruction ret uses the procedure link register X30 to return when no register is specified. And that makes sense. First, save the values of X10 and X29 and X30 in the stack pointer. Then I do my programmer thing, and then I load back the values to get back to where I was at the beginning when I began doing the thing, and then I return. That is, I go back to what was the value and to what is the value, update the program counter by the value by the address stored in X30 register. The return instruction ret30 is the same as just ret. Yeah, that is right. The branch and link instructions are used to call subroutines. Branch and link, branch to link, register link, BLR. BL for branch link, BLR, branch link register. Okay. The branch and link instruction is identical to the branch instruction except that it copies the current program counter to the link register before performing the branch. performing the branch. The branch to register and the link instruction does the same thing except that it branches to the address contained in a register contained in a specified register. This allows the programmer to copy the link register back into the program counter at some time later in the at some later point with the return instruction. This is how subroutines are called, and how subroutines, by subroutines they mean functions, subroutines, and resume executing at the next instruction after the one that called them. Syntax is this: target. The target address can be any label in the current file or any label that is defined as dot global or dot global global in any file that is linked in with a range of 125 MBs. That is unconditionally branching. The target address can be any label in the current file or any label in a file that is linked to the current file. Okay, BL stores the program counter plus 4. That is the next instruction that was supposed to run if it was not for the BL for the branch instruction, and puts the target address into the program counter. Saves the address of the next instruction in link register 30, then load PC with new address. BLR, it loads XN into the program counter. That is the only thing. The following C code uses the printf function from C standard library to print a message to standard output. Yes, the equivalent ARM assembly code uses the BL instruction called printf, called printf section in read-only data. Put the message this ASCII is hello world, and in the text we have dot type, a main function, and global main. Main is a global function, and then store the x29 and x30 somewhere, and then print function hello world. Note the following call to the print function will change the link register, but we saved it on the stack. Yes, load into the zeroth register, them, and then branch link to the printf function. Now move after printing, move 0 into the zeroth register, and then load the x29 and x30 registers back to their original value at the start of the program, and then update the stack pointer accordingly, and then return. A The C compiler will automatically create a constant array of characters and initialize it to hold the message in the read-only data.ro section. Note that strings in C must be null terminated, meaning the last character must be 0. The compiler does this automatically. The compiler directive .exkils allocates a null terminated string in memory. The program will load the address of the first character in the array into register 0 before calling printf. The printf function will expect to see an address in x0, which it will assume is the address of the format string to be printed. By convention, when a function is called, it will expect to find its first argument in RO. There are other rules which AArch64 programmers must follow regarding how registers are used when passing arguments to functions and procedures. These results will be explained fully in Chapter 5, Section 5.4. Example 8. Uh, show shows how the BL instruction can be used to call a function from C standard library to read a single character from standard output. That is crazy. By convention, when a function is called, it will leave its return value in R0 using the BL instruction to read a character. Yeah, BL will branch call a subroutine essentially, and the return value of that subroutine will be stored in the x0 register. Suppose you wanted to read a single character from a standard input. This can be accomplished in C by calling the getChar function from the C standard library as follows. C is getChar. The above C code assumes that the variable C has been declared to hold the value of the function. In A64 assembly language, functions always returns their results in x0. The assembly programmer may then move the result to any register or memory location they choose. In the following example, it assumed that W9 was chosen to hold the value. Okay, first I called this and then I put the value of 0th register into the ninth, and I am using W because a, a character is represented by 4 bytes, which is W, a word. The full assembly program below accepts one character of input and then prints it utilizing the getChar BL. Okay, format is string. What does it do? Format string is a string. Okay, like this. And now in the text, I do type main function global main, and inside main I do this. Okay, what am I storing? I am storing the string this. I am storing the string this. Okay, stp store pointer, store the state, current state, frame pointer, and the link register onto the stack. Then call the getChar function. Then move the character from the 0th to the ninth register. Now I want to call printf with this. Now load the address or the literal address for the formatted string onto the 0th register as the first argument, and move the value from the ninth register to the first register as the second argument, and then call branch off to the printf function. And then after I know that at this point the character has been printed, now I move word 0, move 0 into the first one, and then get back the state as it was, and then return. Nice point to test our skills. Dot read only data, read o data, and inside that string which has the characters char c backslash n, and it's like dot has keys. Yep. And then dot text. In the dot text section I have, well, before main I have to define dot global, as main is the dot global, and now main is this. What is main? Main, what does main do? Main first stores s store pair of 29 and x30 onto the stack pointer by decrementing it, that is increasing the stack by 16 before the function, before the calling the thing. And then I want to call the bl get char label, and after that I know that the character will be in the first register 0. Then I will move the character into the ninth register from the register 0, and now I want to pass in the arguments to call the printf function. And for that, the first one will take the string thing. So load load the into x0 the literal value of the string and move into w1, that is the second argument, from w9, and then bl printf, right? This is done. After that, let's load back the state as it was. ldp load back pair 29 and x30 from the program counter and increase the program counter by 16. That makes sense. And then just return. Yes, that seems correct. GCC, I said text.s, read only data, unknown directive, shit, and okay, this is a problem. I will be storing this inside the text section itself, not in some extra read only section. Let's see now. Okay, linker command. There is an error. Get char reference from main. Print reference from main symbol not found in the architecture AArch64. Okay, let's just make an object file and link them later. GCC text dot s and the output should be text dot o. The linking does work, and now I want GCC text dot o and the output should be text. The linker sheet. How to link std lib standard library in GCC. Linker GCC can't find standard libraries in options. GCC.gnu. Oh shit. Okay. Oh, why is there a music thing here? Library. Yep. A file that does not end in a special recognized suffix is considered to name an object. To name an object file or library. Object files are distinguished from libraries by linkers. Let's see. Um, Standard library, nothing. How to link? Wait, let me use clang. Clang is the one giving me error. Right, text.o. Same error. Okay. How to link standard library in GCC compiler for assembly code which is calling printf and get get c. Wait, is it get c or get char? It is get char. Yep, get char. Okay, here is my code which stores the things. It assembly link as assembly make object file out of this or directly with GCC. That is what I did. This object file and this. Okay, now link GCC output should be this and no start files. This ensures the default C runtime CRT0 isn't included because you are managing the program. entry point yourself. Wait, no start files. Seems like the thing I should do. clang text dot o. The output should be text and no start files. No start files. Okay, referenced from main in text. Load symbols not found for architecture. This okay. Ooh, I am getting error. Error indicates that the linker cannot find the printf and get char symbols. This happens because the linker isn't linking the standard C library libc by default when you use the no start file option. The no start file option excludes the default startup files, but you still need to explicitly link this file lc. Okay, lc to link the C file. Still the same error. Unidentified symbols. Explanation, no start files. Additional considerations. Entry point. So do I define the entry point as main? Entry point as main. Still the same error. Okay, what else can I do? Verbose output for debugging. Verbose. Yes, I am facing issues. Miss. Yep. And yep, here are my issues. The error suggests that the linker cannot find these two files, these two labels. It can happen for a few reasons, such as incorrect references or missing libraries. Let's address the issue systematically. Root cause. Printf and get char symbols reside in the C library. libc and their references must align with how their linker expects to resolve them. On Mac OS, standard library symbols often require linking with the system-specific libraries. Ensure correct references. In your assembly code, declare printf and get char as external symbols. Okay, what I can do is mm, make a C file, print.c, which has include stdio.h and and int main void and printf hello world. Now I can see the assembly code for this thing, right? GCC make this into for assembly. What do I do for S? I put the capital S and print C in, and the output should be print.o. Now I will get the assembly code. Why did I put .o for some assembly code? Doesn't matter. Dot print o, and here is the assembly code for the thing. This is like bad. Print C, where is print o? Print o, where is print o? Print o, and I want to replace this with print s. And now where is print s? Here is print s. Okay. Now section build version global main. Okay. P align main cttt. How am I calling? This is what I did. This is exactly what I did. Okay. This is cool. Then I move the stack pointer. Move the value of the stack pointer into 29. Okay. And then this. I declare this in the text section itself. Okay. And when am I calling printf? I'm calling printf here. It has to start with an underscore, it seems. Okay. And what was the name of my function? Text.s. Seems like it has to start with an underscore, and this might now work. GCC text.s, and we have an error. Somehow illegal text relocation to string linker command. Okay, GCC text and in verbose mode we will see the error itself. Apple Clang version. A lot of things you can't even read. Okay, next text.s. Okay, what is the problem? That I am calling this string thing in here, in here. Is that the problem? Linker command failed. Okay, illegal text relocation in the main plus 30 to string. Okay, and where there is this problem. Now, if I were to use the dot data section to store this, then I would not be able to get this here. I can go to the sum.viewPrint.s function to see how it is managing L1 string this, and then I get the address of the page into the zeroth register by stating the name of the label, then at the rate page, and then adding to the zeroth register the page offset of that label. Huh. So instead of doing this, I should do ADRP address of page by doing label into dot this page and then add save into the zeroth address, add to the zeroth address what string at the rate page of gcc text dot s. It compiles dot okay gcc text dot x, and the output should be text, and now dot slash text. Okay, I have to enter something. D, our char is messed up. Did I use ASCII's text dot s? There has to be a null terminated string. I did use ASCII's. Then what is the problem? They also used ASCII's. What is the problem? I have provided the first argument properly, then the second argument properly, right? Yep. I took the output of the first argument into the ninth register, and then from the ninth register to this, or I can just take it directly in the first register and remove this step. Okay. Maybe I should do this. Yes, I should do this before messing up the register. So I get the character in here. Then I return at the end. GCC text dot slash text. I enter some character, but I don't see it somehow. Well, this part is working perfectly. What about this? Is it because of, let's see. Okay. And text dot x. Let's replace the W with an X. And let's see. Did not work out. Ah, what the uh, text dot move and gcc dot slash text and enter a character G and nothing. Okay. Hmm. Compare and branch. Yeah, at this point, move, move, and call printf bl, and then move 0 into 0 to return 0 0 0 0 0 0 text dot s. It takes only 4 bytes, so w. Mhm, 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 mhm. Let me do something. Let me store instead of that some literal value, some value that is 65, which is the value for character A in that register. And let's see, do we see A or not? We do not. So is there some problem with that? Text.s. Uh, Second argument here. First argument is going there properly. It has to be percent %C, right? Yep, percent %C. Hmm. Shit, I have to ask ChatGPT what is wrong. What is wrong with this code? The first argument for the print, hey, for the print f function is going for properly, but the second, but I am not getting the character I want in the placeholder %C. And one more thing, let me change it from W to W0 so that it does not fuck me over. Okay. The issue lies in how the character returned by get char is being parsed as an argument to the printf. Specifically, the W1 register contains the character returned by get char, but printf expects the argument in specific registers. W1 register contains the first argument for a function is passed in this. The first argument is passed in this. The second argument is passed in 1. Okay, your code is incorrect. Code incorrectly moves the character into W1, the lower 32 bits of X1, but does not properly place it in X1 before calling printf. Why? Okay, now we'll get char and move character W1 second argument and get the address in the first argument, then call printf. Call. You did not fix anything. For printf, the first argument for format is string in this. The second argument print character to print is placed in X1. You literally have changed nothing. Literally nothing. This is what is here. Well, I changed and W0. This is what is here. Literally changed nothing. Area this. Um, Register usage. Ensure the character is explicitly moved in W1, which is the lower 32 bits. of X1 register because printf expects it in this register as the second argument. Calling convention. Follow the ARM64 procedure. Call its status to pass arguments in the character registers. Explanation. Yo. The first thing you do when you see an error, recompile the program and run it again. A will have to solve that problem later. And for now, end ending the stream.